Good morning from rainy Austin, Texas. I'm Sarah Cook, Senior Marketing Communications Manager for Caringo. Thank you for joining us today for a deeper dive into object storage. This webinar is geared for application developers who want data protection, high availability, and high performance built into their products. Before we begin, let's review a few housekeeping items, despite the fact that I absolutely hate housekeeping. If you have any questions during the webinar, feel free to type those into the question field. Our speaker today, Ryan, will try to answer all of your questions. If for some reason we can't get to your question, we're happy to chat with you after the webinar, and you can always reach us by emailing info@caringo.com. We have a few polling questions during the webcast that we'll be pushing out because we'd like to hear from you, and we also have several links to videos that you might want to check out. I'd like to kick off today's webinar by introducing our speaker, Caringo Product Manager Ryan Meek. Ryan has worked as a developer, tester, training, sales engineer, and now product manager in the object storage industry, and he's also one of my favorite colleagues. Good morning, Ryan.
Thanks, Sarah, and hello, everyone. Good morning or good afternoon, depending on where you are. We're really excited to be with you today for a deeper dive into object storage. Like Sarah was saying, much of the presentation is geared towards developers, but it's actually also, I think, high level and technical at the same time as general object storage information. So while we will get into the weeds a little bit, I think it will be generally useful information really for anyone looking at object storage, needing an introduction, and then needing a little bit more information about how it's actually all put together. So just beginning at the basics, what are objects? Okay, so objects are data and metadata. We use the word encapsulate quite a bit when we talk about that, and that just means that data and metadata completely make up the objects, and the objects are portable. So this is as opposed to, say, a traditional system where data might live on a file system, and then metadata about an object might live on a database, and then there's some relationship that needs to be kept. In object storage, metadata and data should be encapsulated in the object. So what is object storage basically used for? Why does it exist? Well, the short answer is data protection, high availability, and high performance. So the data protection part is really because once you have the metadata and the data encapsulated in the object, you can integrity check the complete set, and then you can continuously check those hashes, and you can ensure going forward objects are the objects that they were stored. Not only that, but it makes the collections inherently self-healing because you can continuously in background processes be verifying that the data and the metadata haven't been changed or haven't been corrupted. High availability is actually built in to the architecture because objects are either replicated or erasure coded, and the data protection is done in such a way that you will have availability to those objects even if hardware failure occurs. Hardware failure is just normal when you're dealing at scale. Disk drives fail, servers fail, entire racks can go offline because of power, and so your whole architecture needs to have high availability baked in from the beginning. If you're replicating an object, for instance, 3 times for data protection, and a server goes down, you still have 2 instances available, and that high availability follows directly from the data protection. By the same token, if you're doing erasure coding, you'll have the number of slices that you need available even in the face of disk failure or server failure. And high performance follows from those two because, as you can tell just by thinking about it, if you have a replica that goes offline and you need to read another replica, that's going to be fast. The system won't be, for instance, doing a RAID rebuild. The system won't be doing kind of an old school swap around virtual IP addresses, DRBD, no swizzling under the covers will be happening. There'll be a first-class server performing a first-class read on a first-class replica of a first-class object, and that all happens at runtime. HTTP is the most common. Go ahead.
Brian, somebody in the audience asked if they were able to download the slides for this presentation. So I just want to say, if you want to email us at info@caringo.com, we can work on getting you some information. So don't hesitate to ask us. We don't have them publicly available, but we're happy to work with you on a one-on-one basis.
Great. So HTTP is a really common front end for object storage in general, and it is the front end for the object storage at Caringo in particular. And it was a choice in the very beginning made for openness and ease of use. It's one of the most common protocols in the world. All the modern computer languages have standard libraries that can deal with it and facilitate development. And it speaks to making data available going forward. So, this isn't an API that will expire. This is an API that will be available and well understood for years. And so the combination of data protection, high availability, high performance, and HTTP combined with requirements in cloud storage areas really makes object storage a perfect complement to cloud storage. Cloud storage, you typically need to be able to scale to billions of objects or petabytes of data in a multi-tenant environment. Object storage scales inherently and is high performance, and with HTTP on the front end is already the protocol that's coming in to make the requests in many cases. So that's actually a good intro for why object storage, some of the value adds for object storage, what it is, why people use it, what it's good at. And what I want to do is get a little bit more into technical elements of object storage systems and some of the differentiators between them. So there are a few different approaches out there in the market. One is an approach that's much more like a software appliance. That happens to be the approach taken at Caringo. But there are also approaches where you can say install your own operating systems, install your own file systems, and sort of administrate machines in the system more directly. Our approach at Caringo has always been to purpose-build a system so that it is very low administration and appliancize it. So purpose-built object devices that don't require RAID, don't require LUNs, or additional relational database. That basically brings down the cost of administrating it, and it increases the ease of use. There's certainly other arguments that could be made for going the other direction, but we generally see that adds unnecessary complexity. The other things to really look for is, what is the operating environment for the actual object storage system on the servers? Are they set up to run from RAM? Are they subject to swapping to disk? Are there other processes that may be running on those servers, or are they fully dedicated? And do those either software appliances or object processes also incorporate the ideas of being able to spin down disks when they're not being used? In the Caringo case, we have a strong preference for appliancizing core servers for running from RAM for performance, and for spinning down disks in general when they're not needed, when they're not being used. But it's definitely something to look at and be aware of.
We have another question
go ahead.
on what you were just talking about, Brian. So the question is, so do you need to buy new servers to run this software, or can you use the ones that are already in your data center?
So that's a great question. And I think the answer is both. You can certainly run object storage software in many cases on standard servers. Certainly in the Caringo case in particular, it's built for running on x86 standard servers. And it's built to run on really any combination of form factors, densities, and drive sizes. So whatever, server or form factor or performance factor that you want to target to hit, you should be able to do that with the software. And one of the things to look at when you're putting together an architecture for how the servers would be used or how the servers would fit together is, how many different server types or how many different functional types need to coexist and cooperate to form a valid object storage cluster. In the Caringo case, we've gone to quite a bit of effort to make sure that all the servers and all the nodes can also be load balancers and service requests. So they also have HTTP on the front end. In some cases, you may need special case load balance. In other object systems, you may need special case load balancers or special case front end to service requests, front end, web servers. But in our case, we actually go out of the way to make all the core nodes handle service requests and for all the core nodes to be load balancers as well. By the same token, some approaches may require additional hardware for multi-tenancy or additional hardware for multiple domains. It's another thing to look at when you're sort of estimating how much complexity you may be getting into with an object system. The Caringo case also makes multi-tenancy, metering, and access control in a complete sort of cloud environment available on all nodes. So basically, the core node is able to service all these different types of requests and simplifies the architecture tremendously. So we brought up data protection at the very beginning. And so what I want to get to on this slide really is the continuous protection element, where you can see an artist's rendering at data protection through replication, which is where an object gets turned into multiple replicas, and data protection through erasure coding, where an object gets protected with really slices. You can think of it as object level RAID. And an object would get protected through data slices and parity slices. For instance, an erasure code of 5.2 would be used to express 5 data slices and 2 parity slices. Those slices would be distributed to different nodes on the system, and an object could be reconstituted from any 5 slices. So 2 drives could fail or 2 servers could go offline, and there would still be full availability to that data. So when you're looking at systems in general, it's interesting to note, can they do replication? Can they do erasure coding? Can they do different kinds of erasure coding? So for instance, we can do 5.2, we can do 10.2, we can do 15.4. It really just depends on the level of data protection and the number of slices you want in your environment. The other thing that's interesting is some systems need additional rings or additional deployments to handle different coding levels or replication levels. And we actually can do the replication and erasure coding data protection in the same clusters. This is actually a very key element, because the last thing you want to do is have to add a new cluster for a data protection strategy. by the same token, you can add servers and at the same time not worry about those data protection levels. So you could add servers to a 5.2 erasure coding cluster and not introduce any complexity. You can do it at runtime.
So, Rod, we have a couple more questions. One is, could you explain what you mean by elastic content protection? That they've seen that term used by Caringo before. And then also, since you have continuous protection, do you still need to put in a backup system?
Yeah, so that's a great question. So continuous protection, I mean, we consider that the combination of replication and erasure coding. And actually, that's also combined with continuous integrity checks in the background. So some systems rely on a lazy check, or they'll have a third replica in the background and just not be self-healing in the background, for instance. So it's really continuous background processes guaranteeing through integrity checks, replication for erasure coding, and erasure coding. And also there's, in many cases, a threshold that makes it optimal. So for instance, replicas below 1 megabyte and erasure coding above a megabyte might be ideal combination. And let's see, and so if you're doing, and then the other question was really about backup. If you're doing data protection in a scale-out environment and you have billions of objects and petabytes of data, the fact is that these are really built in cases, for cases especially, where those backups would just never finish. And so the quick answer is really no. You don't have to back it all up. And if you actually need the DR copy, the way that that's done is keeping and that's actually a perfect segue into the next graphic on the right-hand side of the screen. What you do is you would set up a different cluster at a different location. So actually only the changes in the objects or the additional objects would get propagated between clusters. You can set them up so that the replication is happening in both directions. And so you always have a fully up-to-date, or as fully up-to-date as your network connection will allow, a copy of all of that content. This is another place where it comes back, the object location independence comes back, because the data in these clusters can be routed worldwide, and the data is location and application independent. So what do we mean by that? Well, the object isn't tied to a place on the network. It's not tied to a certain machine or file system, and it's valid wherever it is. So if that if that object is in a different region, you can still view it. If you have permissions, you can still act on it. It could be used by analysis as well as reporting, as well as the application, and then you could actually go do, so for instance, Hadoop jobs in the background and use the same content.
Great. We've got yet another question coming in from our audience. And we love it when y'all are interactive. And Brian always tells me he likes the tough questions, so feel free to bring them on. This question is, so it's good for reads. What about writes like IO-intensive apps, for example, VM databases?
Yeah, that's a great question. So it turns out to be a perfect repository for VM snapshots and can be used as an external snapshot repository. IO-intensive apps, especially like online video or security video, you could have 200 different cameras writing 200 different high definition streams. It's write, multiple writes and no single point of locking in the cluster. So you have the complete IO of each server, in a 10 gig environment available for the processes. Databases, we generally consider a workload that's not the best workload for an object system for the simple reason that it's usually one file that's continuously changing. So I have actually heard the object storage perfect use case as everything except databases or perhaps indexes. So it's great for IO intensive, it's great for apps, it's great for VM snapshots, but it's probably not the best thing for actually the database files that are being continuously changed by continuous transaction updates. So actually, let me call out explicitly for any more questions on that slide, because that was actually a pretty big slide. There were quite a few elements on that slide that were interesting. I'll just pause for a moment and put these pictures back in front of you to jog your memory. So these really are the nuts and bolts of object storage. You've got devices with replicas or erasure coding slices. You have architectures that are either flexible or not flexible. You have data integrity and data protection by replication or erasure coding. And you have object portability and application dependence in the full multi-tenant namespace.
So we've launched another voting question asking you how you use metadata in your field. And this is a topic at Caringo headquarters on a daily basis. So we'd really love your input about how you're using metadata in your organization.
I'll go on to the next slide now. So we talked about HTTP on the front end. And so let's just talk a little bit more about specifically what that means. So it turns out to be a perfect protocol for object storage and for objects that are composed of metadata and data, partially because the container in HTTP is roughly a MIME message, and MIME messages are roughly headers, 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 and data. So it's really a protocol that is perfectly suited for object storage. And the interface is roughly what people call a CRUD interface in many cases for create, read, update, delete. And those methods map to HTTP post, put, get, head, and delete. So your creates will be generally your posts and your puts, your reads will be your gets, and your deletes will be your deletes. Head in that case is interesting because we consider that an info on the object. That's a method that will return the metadata for an object and not the data. So for instance, if you have a a 2 GB file and you would just like to see the metadata that's associated with those objects, you can do an HTTP head and it will service the request with the headers or the metadata from that object. It also turns out to be a great place. Go ahead.
We have another question, and I love the way it was written. There's a number of O's on the first word. So, not best for Oracle or SAP?
Yeah, so I would not use it as the data backend for the Oracle binary files, for instance. So your DBA won't want to put the actual Oracle data files on it. They'll probably want to put a SAN there. But in many cases, if they're having a performance problem or if they're having a space problem or a growth problem in the database, whether it's Oracle, and all the same things I think here apply for Oracle or say SQL Server. In many cases, it's because the database is actually being used to store unstructured data or basically fields that are very well suited to become objects. For instance, pictures, photographs, videos in some cases. People are actually putting that in the database. And it's much more efficient to put a UUID or a name to an object and have an object storage cluster as a target. That, in many cases, has been the answer to how to make a database faster, how to make the scaling, how to sort of positively impact the scaling problem. And it's actually the driving force between many large installations. So a couple of social media sites in general that we work with, a couple of digital evidence sites in particular. Now, they have databases that were just out of control with the size and the load. And it turned out that moving the unstructured fields from the database to an object storage cluster was the thing that really helped them scale. So that's a great question. So back on the REST content API, what kind of headers or what kind of metadata is actually common for objects? I think it would be worth it to say a few things about that. So the real common things are elements like file types or content types, content dispositions. Those are sort of standard HTTP metadata. We also include, and many systems also include, the ability to store custom metadata. And custom metadata is metadata that matches some prefix so that the header will actually be persisted with the object. You don't want to persist every header that comes in from HTTP. Proxies and HTTP infrastructure are fairly liberal with adding headers to requests, but you can put one in. In our case, star meta star is a matching pattern, and so star company name, meta, some kind of video or some kind of file or descriptive properties about that object is the general pattern. And then actually those headers can be used to drive policy management and compliance downstream. So whether that object can be deleted, whether that object can't be deleted for some number of years, for instance, is common, or an upstream application like a Veritas semantic enterprise vault or a Commvault may use that mechanism to indicate content that can't be deleted, for instance. We call that, many people call that WORM, for write once, read many. So are there any questions about, the REST content API, HTTP in general, how to include metadata, headers on objects, how that works? I will just keep moving on.
So we do have a question that came in. So why would you code applications to object storage solutions? Okay, so that's a great question. In many cases, applications are coded directly to databases or file systems, and so they tend to suffer from cases where the data is hard-coded to its location. That happens in databases and file systems. When data is hard-coded to its location, or when the application knows it has to go to some specific location to get the data, the architecture question quickly becomes, what happens if that location isn't available? Where are the other locations? How do you sync objects to those different locations? And so in an object system, the entire system is really addressable or targetable as a URL or as a location. So for instance, clustername.mycompany.com. And then that request can be routed through load balancers and HTTP infrastructure through all the same mechanisms that requests are routed on the internet. So, the structure of the internet was really about how to get requests serviced in the face of hardware
failures or location failures. So you can actually route requests to their content. You can route the request to the content in a primary location, in a secondary location, in a roll-up location. So in many cases, it's about location independence of the data. In many cases, it's about the high availability we were talking about. So, just having an application that stays up online when disks fail, when servers fail, when racks fail, that's tremendously useful. For the administrators that are servicing those applications, when disks in these clusters fail, if it's a RAID-based system or a SAN in many cases, the whole system's in a degraded state while a rebuild is going on, or it's just left in a state that's at an elevated risk for further failures. But in an object system, disks can just fail as fast as they need to, as long as there's headroom available in the cluster, and administrators can go and say change disks every month. And this is a life improvement for a lot of administrators. When you have a system that you can go do maintenance on every month, as opposed to getting paged and having to get out of bed in the middle of the night, that's a better system. So I think those were the reasons right off the top of my head. I would say the other one actually is exactly what we're speaking to on this side, which is having HTTP on the front end. When you have protocol requests coming in for content, web content or internet content, being able to serve the request in the native protocol of HTTP and of the internet is a huge win. So for instance, you can have people watching videos at home, and that request is being served directly out of the storage. So it's web content that the request is in HTTP. Someone's looking at a video at home. They can even, drag the progress bar around. Those are HTTP range requests that'll slice into the middle of a file. And no additional no additional layer of web servers and relational databases are needed to service that request. So that's really combining the web tier with the storage tier. So it's just tremendously efficient. I think those were three reasons right off the top of my head. I'm sure there's more in there, but we'll go ahead and move on. Anyone can get in touch with us if you'd like us to go into more depth on any of these points. And really, I just wanted to call this out pretty quickly before we go. I mean, one of the things to think about if you're taking a deeper dive in object storage and if you're looking at different systems is all that data transparently available and usable in a big data context? In our case, you don't need any additional servers. You can fire up Hadoop, and Hadoop jobs and Spark jobs, for instance, will run, and they can access content directly in the object storage clusters, in the swarm clusters. And that makes it really an ideal repository, not just for unstructured data, which is where many people started with object storage, but also for structured data. In many cases, IoT data is highly structured, and it's important that you can handle tens of billions of objects and still be fast and not need to run a backup, still handle requests and even handle requests in the native protocol which they were made. It's all important that it works together. And I just wanted to call that out as sort of one extra thing to be aware of when you're sort of future-proofing your architecture decisions with object storage. So with that, I think I wanted to call out for another round of questions. This is just really about the wide range of use cases and markets. I think we could go into quite a bit of depth about any one of them, and we've mentioned a few of them here, but wanted to be sort of available real time for any other questions that you might have about this content. And of course, you can get in touch with us later if you have any further questions.
So we have a question. Is there proprietary code for object storage? Is that required, or is it all open? And what are the differences in the different types of object storage?
Yeah, so that's a great question. So SDKs, maybe in the first object storage systems that came out, you might think of it all the way back to, say, the Centera from EMC. And, you know, the approach from EMC was highly proprietary, right? The EMC Centera libraries were proprietary libraries, and so when you wrote applications with them, you were taking some other company's proprietary code, and it really made your applications dependent on those. The Caringo case in particular, and I don't think I can speak directly to some of the other SDKs, but the Caringo case in particular, the SDKs are all open source, and they're generally standard open source HTTP libraries that have been wrapped with sort of common constructs that are useful in an object storage high performance environment. So they'll do things like reusing sockets. They'll do things like handling, you know, metadata collections and keeping pools of nodes that are available, taking nodes out of pools if they may not be available, and just sort of facilitating all the things that you would want to do if you were writing your own layer, which you can, because it is HTTP. So if you're in a language that isn't in the provided SDK, there's absolutely nothing to prevent you from writing to it. It is all open. It's all open source. And if you make improvements, or if you would like to have those patches available in future versions, you know, we're always happy to work with people and help their development environments and simplify them. So that's a great question.
We've had a couple more roll in while you were answering that one, Ryan. Is it platform and storage media agnostic?
It is. So if you consider all the different x86 standard servers and different disks, different disk types, different, it's generally spinning disks in, you know, direct attached storage, but there's nothing that strictly limits it to that. That's probably the most common. Yeah, so spinning disks are probably the 99%. By the same token, as long as the storage system looks like a connected device to Linux, it will be storage media agnostic. So it will have to follow certain. It should be read-write, for instance. But yeah, I would say it's 99.something9 spinning disks is probably the best way to say that.
And then we also have another question. How would you share something on object storage and apply permissions?
So that is pretty easy to do. You can share something on object storage in many cases if you have the universally unique identifier or the name of an object. So you can actually send a link to the object instead of sending the object itself, which is kind of fantastic, especially if you do it in email. You don't have to send terribly huge attachments. And really, permissions can be applied in many different ways. They can be applied on the objects themselves in metadata headers. They can also be configured in a general cluster along with LDAP or Active Directory, so that users need to have permissions to domains and buckets, for instance. So it's actually very flexible in that case. I think in an enterprise environment, Active Directory and LDAP are very common. in a web cloud environment. They're also common, and that can be done at HTTP level authentication as well. So there are many different options for how to configure a cluster. And do we have links to the open source? So the open source software that I was talking about is the SDK, and it is available from Caringo Connect. So we would be happy to give you a copy. Just go ahead and register at Caringo Connect, and we can help you get started right away.
Great. You may have set a Caringo record for the most number of questions coming on a webinar, Ryan.
I love it.
And I think we've got one more about how quickly can an application be developed when you're using object storage solutions?
And that's a great question too. And I think the answer really just depends on the application and how, really, whether it's a greenfield new application or whether it's a legacy application. In general, I've seen everything from 1 or 2 days to 1 or 2 weeks. It's usually less time than people expect. The interface is very simple. HTTP is very well understood. There are very good HTTP libraries in every language, and the SDK actually really facilitates development time as well. So I think the very short answer is it depends. I think the longer answer is some combination of requirements and whether it's a greenfield application or a legacy application. But it's a good process, and it goes very quickly, very quickly.
And we have another one asking about how does this work with Flash? Is there difficulty there?
No, actually. So flash drives look just like regular drives to the Linux kernel. So if you load up a standard server with flash drives, you can expect the performance benefits that Flash provides. So that's one of the great things about using sort of standard x86 servers on a wide variety of hardware. We have specific use cases where people have loaded up, have servers be fully Flash loaded for all the high performance that those use cases sort of demand. So it's a great platform for Flash.
So
any other questions on the line there, Sarah?
That is all I see. Please don't hesitate to reach out to us if you have more questions, though. We love to quiz Ryan.
Thanks, everyone. We really appreciate your time here. It's been a real pleasure taking you through a deep dive with object storage. Please get in touch with us if we can answer any more of your questions. We'd love to hear them. Thank you.